So let me begin. So these lectures are mainly going to take place in the discrete setting, because we're going to talk about discrete signal analysis. And in real life, signals are discrete and finite. However, one point that I want to stress over and over is the unity of mathematics, connections between discrete, continuous, and arithmetic ideas. Okay? So one of the things, so every mathematician is annoyed by something. And what annoys me the most in mathematics is when people divide mathematics into different areas. I think mathematics is one coherent whole. And another thing that I heard many, many years ago from Jean Bourgain, the field medalist, is that he told me that you have a choice as to which problems you work on, but you don't have a choice as to which techniques you will need to use to solve them. And this is why it's important not to divide mathematics into distinct pieces. So I'm going to start with, in a continuous setting, to give you a flavor of how I think about these things. But then I'm going to quickly specialize to the discrete setting, where I'm going to introduce and prove everything. Also, I deeply dislike talking to myself. So if you have any questions, please ask me. Okay? If you want to ask a question in Ukrainian, I understand Ukrainian very well. Okay? I'll probably respond to any question. All right. So one of the deepest and most central problems in analysis is the classical restriction conjecture. Okay? All right. Classical restriction conjecture. And what it says is that if you take a Fourier transform of a function and you restrict it to a sphere, and you take the LR norm, then this is bounded by a finite constant times the LP norm of a function in a certain range of exponents. Okay? And so, again, if you haven't worked on this before, I don't expect you to grasp all the intricacies of this problem, but what I would like for you to notice is that there's clearly something non-trivial going on, because we are taking a function, taking its Fourier transform, and we are restricting it to a set of measures 0, right? A sphere is a set of measures 0. So it's not a priori clear that this sort of an inequality even makes any sense. Okay? However, it turns out that it does, and the conjecture range of exponents is what I wrote down. So this conjecture was solved in 2 dimensions in different settings by Charles Safferman and Anthony Ziegman. But in higher dimensions, in spite of brilliant work by numerous mathematicians, including the ones listed here, the problem is still open. In other words, the precise range of exponents is still open. So why am I telling you about this? After all, these lectures are about signal recovery. Okay? And this is because there is a signal recovery perspective on this conjecture, which has led to some ideas that were implemented in the discrete setting. Okay? So the point I'm going to try to make in the next couple of days is that ideas from analysis from the continuous setting influence ideas in the discrete setting and vice versa. Okay? Is everybody with me so far?
Could you explain what is this C, this index PR? Is this like for each P and R there exists this C that this equality holds for all functions?
That's correct. That's correct. So this is a norm inequality. So think of taking a function and taking its Fourier transform and restricting to the sphere. This is a linear operator. Mm-hmm. Yeah. So this is a functional inequality. And you should think of CPR as the norm of this inequality.
Oh, okay.
So it's the norm of the restriction operator from LP to LR. Mm-hmm. Because, of course, abstractly at least, we want to take the best constant, which is the norm. In real life, best constants are almost never to be found, but that's a different story. Mm-hmm. Mm-hmm. And so let me give you a signal recovery perspective on restriction, because it's going to influence a lot what I'm going to say today and tomorrow. So suppose that A is a compact set It doesn't have to be compact, but I just want to keep things simple. Dimension is at least 2. The measure of the set is positive. And the Fourier transform of the indicator function is known, except for the frequencies in the delta neighborhood of the sphere. So in the annulus of radius 1 and thickness delta. Okay, so we take the indicator function, we compute its Fourier transform, and then we lose the frequencies in the delta neighborhood of the sphere. Okay, can we recover the indicator function? Okay, so let's proceed in the most elementary possible way. So what do? We write the indicator function, and we write it as the inverse Fourier transform of its Fourier transform. Okay? And then we divide this integral into known frequencies and unknown frequencies. Okay? And so think about the integral over the unknown frequencies. So common sense in mathematics is your friend, contrary to popular belief. Since these frequencies are unknown, we can't possibly do anything intricate. All we can do is make some kind of an estimate and hope for the best. Okay? And remember what we are aiming for. We are aiming for something that doesn't sound incredibly plausible. We're not trying to get the indicator function of a set A approximately. We're trying to get it back exactly. Okay? So what do? We're going to take the second term, we're going to estimate it, and see what happens. Okay, does the setup make sense? So we apply Holder's inequality, and we bound the second term by the volume of the delta annulus times the normalized LR norm over the delta annulus. Okay? And here comes an interesting point, which is probably not emphasized enough in multivariable calculus. Okay? So what does it mean to integrate over a sphere? So depending on which book you used when you took multivariable calculus, it might have been introduced as, where you take spherical coordinates and then you immediately integrate in local coordinates, etc. But another way of thinking of the integral over the sphere is just to thicken the sphere by delta, divide by the volume, and take the limit as this thickness goes to 0. So to me, this is what it means to integrate over the sphere. Does this make sense? Yeah. All right. And so if delta is small enough, it stands to reason that whatever estimate we had before better hold now if delta is small enough. Okay? I know I'm burying some details under the rug here. Oh,
yeah, I missed an hour. I thought it's the same time as me.
Don't worry about it.
Sorry.
So let's assume that the restriction estimate holds. Okay, so then this LR norm is bounded by the CPR that we discussed earlier, times the volume of the annulus, which we brought over from the left, times the LP norm of the indicator function of the set, which is just the measure of the set raised to the power of 1 over p, right? Because you compute the integral of the indicator function raised to the power of p. Raising 1 to the power of p is not very interesting. So we just get the volume of A or measure of A, and then we take the pth root. Okay. And now, okay, so what do we do with this? So by assumptions, if the restriction conjecture is correct, we get this bound. Well, what if it's less than a half? What if this thing is less than a half? Then let's go back to over here, right? So this is the integral over the known frequencies, and this is the integral over the unknown frequencies. If the second integral in modulus is bounded by 1/2, then we just take the first integral, compute its modulus, and then round it up to 1 or down to 0. imagine we compute this integral and we get a value of 0.6. Well, then the value must be 1 because the second integral in modulus is bounded by a half. Well, or if we compute the first integral and its modulus is 0.4, then it must have been 0. So we actually get exact recovery of the indicator function of a set. Okay? Does this make sense? So not only do you get exact recovery, but you get it, so in the continuous setting, of course, but when we go to the discrete setting, you'll see that not only does one get exact recovery this way, but the mechanism is incredibly efficient. It's very fast because computing the discrete Fourier transform is very fast, right? And all right, and there's one more point to be made. Let's go back to this inequality. This inequality is in general very sophisticated. In fact, as I mentioned, it is not even known in the whole range of exponents in higher dimensions. But suppose that p equals 1. Okay, then I claim that this inequality always holds with constant 1. Why is that? Because let me remind you the definition of the Fourier transform. F of c is equal to the integral of e to the minus 2 pi I x dot c f of x dx. Right? So take the absolute value. And this is less than or equal to simply the integral of f of x dx, which is the L1 norm of the function, right? Which means that if we take the left-hand side of this inequality, we can bound it by, okay, so I lied slightly. I said the constant will be 1. The constant will not be 1. It will be the measure of the sphere. So if this is just a restriction of the Lebesgue measure, then we get, you know, whatever it is, the volume of the bowl divided by the dimension. Or if we normalize it, then we can make the constant 1. Make sense? So this inequality always holds when the constant is 1. Okay? However, in the full range of exponents, take a look here. P is conjectured to go up to 2d over d plus 1. So when d is large, this is close to 2. Okay? So now let's go back to the condition. Remember, the condition was that we want this to be less than a half, which means that up to constants, so the volume of the delta annulus is approximately delta, right? So we want the measure of A to be bounded by delta to the minus P. So the larger the P, the less restrictive this condition is. Make sense? Right? We always have it for P equals 1, but the larger P we're able to take, the less restrictive this condition is, because delta to the minus P is much, much larger than delta to the minus 1 if delta is tiny. Okay, or as I like to say, if delta is 1 divided by the size of the American national debt. Okay, make sense? And then we can recover the indicator exactly. So what you have seen is two things. One is the restriction conjecture in harmonic analysis, which I think is a very important problem. And second, you've seen a connection between this conjecture and the recovery of signals. Okay, so what you've seen is a recovery of indicator functions, but our friends in electrical engineering department refer to them as signals. I have no objection. Okay. Right. So again, the point is that the closer we can take P to the optimal value, the less restrictive recovery condition that we get. Okay. So this is a kind of an analytic introduction to a problem that we are going to discuss purely in the discrete setting, except at the end of the lecture tomorrow, I'm going to go back to the continuous setting to to remind you of my deep religious conviction that all areas of mathematics are connected. Okay? Okay, so finite signals and discrete Fourier transform. So F is a signal of finite length, i.e. it maps Z and D to complex numbers. Z mod n is integers modulo n. Z and D, if you took abstract algebra, it's a d-dimensional module over Z mod n. If you don't know what a module is, it's not going to hurt you at all. Just think of it as a grid. So you have d tuples of elements of Z mod n. Okay? I mean, modules are serious things, just not over Z mod n. Okay? And now we're going to transmit the Fourier transform. So we're going to encode the message by using the Fourier transform. And the Fourier transform, discrete Fourier transform, comes in a variety of normalizations. We're going to choose this particular normalization, and I'll explain why. So here, chi of t is e to the 2 pi I t over n. So this is a standard discrete Fourier transform modulo n, except that everybody seems to have their own favorite normalization. In practice, I've only seen 3 normalizations, where the constant in front is 1, where the constant in front is n to the minus d, or n to the minus d over 2. Each has advantages and disadvantages, and I'll explain what they are. And obviously, they're all equivalent. Okay. Okay. So Fourier inversion formula says that we can recover the signal by using the Fourier inversion. In other words, we can write f of x as n to the minus d over 2. With this normalization, you get exactly the same factor in front in the definition of the Fourier transform and the inverse Fourier transform. And then instead of having chi of minus x dot m, you have chi of plus x dot m, and then the Fourier transform of f and m. Proving this formula is an exercise in geometric series and reversing summations. Nothing more. There's nothing happening here. Okay? In other words, the idea behind the discrete Fourier transform is very, very nice. But proving these formulas really requires no advanced mathematics whatsoever. Okay? Everybody with me? This makes sense? Okay. And here's the basic question in signal recovery. Is can we recover f exactly from its discrete Fourier transform if some of the frequencies are missing? Okay? So as I mentioned before, here is a recovery mechanism of a signal from its Fourier transform, provided that all the frequencies have arrived. But suppose there is jamming or noise or whatever, then this may not be the case. And we want to be able to recover f exactly if some of the frequencies are missing. Now, the first time I saw this, which was, by the way, less than 2 years ago, started working on this recently. I was introduced to this by my co-author, Zita Mayeli, and this has absolutely captured my attention. This is maybe my favorite thing that I've ever worked on, okay? But when she first introduced this to me, I simply did not believe that this was possible. I believed that maybe you can recover the signal approximately, but the idea of recovering exactly, I just didn't believe it initially. I believed it 10 minutes later, but I didn't believe it initially. But you already saw an example, even in the continuous setting, where this can be done, right?
There we had a restriction that this function was like 0 or 1, and maybe here we should have something.
That's right. That's a very good point. So you're anticipating what's going to happen, which is great. When the function is not a 0 or 1 function, we're going to need to find a slightly different mechanism. Absolutely. But at least we know that we can do this when the function is, when the signal is a binary signal, to use that parlance, right? Okay. So the answer turns out to be yes for any signal if the function is supported in a set E. Does everybody know what that means? It means that the function is non-zero on the set E, okay? And 0 outside. And the size of the support times the size of the missing frequencies is less than n to the d over 2. Okay? In other words, if the signal is sufficiently sparse, and if the number of missing frequencies is not too large, then we can recover the signal. And the main tool here is the Fourier uncertainty principle. Okay? All right. So here is, so there are two formulas that we are going to use repeatedly. I don't remember if I decided to prove them or not. In any case, proving them is not very difficult. If you haven't done it before, please try. And if you run into any issues, let me know. So one formula is Fourier inversion, which I've already mentioned, that you can recover the function from its Fourier transform. This is literally an exercise in geometric series combined with reversing the order of summation. Okay? And as I never get tired of saying, when you reverse the order of summation in a finite sum, this is not Fubini. Guido Fubini was a great mathematician, and he did not invent commutativity of addition. This was known before him. Okay? Fubini's theorem for integrals, which I'm sure you've all studied, is a serious thing. And here, reversing the order of summation is just a triviality. Okay? Another thing we're going to use is Plancherel formula, which is that summation of the Fourier coefficient squared is equal to the summation of the values of the function squared with constant 1. And this is one great advantage of this normalization. Okay? All right. So, okay, so should I go through the proof of this, or just be honest? Let's have an open channel of communication. Do you want to see a proof of this maybe very quickly, or no? You guys are okay? Let me skip over this. Yeah, this is good. Okay, so let me describe. Let me just describe a few properties of the Fourier transform, just so you get a feel for what's going on. So suppose that your set S satisfies the property that the Fourier transform is bounded by n to the minus d over 2. Remember, that's the normalization in front, times the square root of the number of terms, times some constant, which we're calling C Fourier. Well, so the interesting thing is that this is, of course, always true, depending on what C Fourier is, right? But this statement is meaningful if C Fourier is a fixed number and capital N is huge, right? But nevertheless, I wanted to write it in this form so that you see the relationship. So now let's consider the L4 norm to the power of 4 of the Fourier coefficients. Okay? So what you do, oh, I did not fix that typo from Lviv. Oh my God. So the S hat, this should be 1 S hat. This should be M, and there should also be a sum in M. I did fix so I fixed half of the time. My apologies. I don't think that there's so many. I don't know why this is there. But anyway, when you sum in M, not Z, what you get is 0 unless x plus y equals x prime plus y prime. Because you're simply cycling around the geometric series. Okay? In other words, the summation of chi of m dot x is 0 unless x equals 0. Here it's x plus y minus x prime minus y prime. Sorry about that. I thought I fixed it. Okay. And if it is 0, you pick up n to the d, and you get n to the minus d times the number of quadruplets in S4, such that x plus y equals x prime plus y prime, which is n to the minus d times the energy, additive energy. Okay? So why is this called the additive energy? It's a long story and not particularly important, but what this additive energy measures is the additive structure of your set. Right? So what does it mean that x plus y equals x prime plus y prime has many solutions? So can you give me an example of a set where this equation has many solutions?
Maybe some regular lattice, like
Right, but we are in Z and D.
some d-dimensional regular lattice.
That is one word. That is correct. But if you just take the whole plane, it will work.
No, I mean, for example, if we take every k point in an
Absolutely. That works beautifully. You just need to make sure it doesn't start wrapping around. Absolutely. That is a great example. And also anything planar will work. Okay? In other words, additive subgroups are great examples of this, right? So this energy measures how much additive structure we have. Okay? And so this additive energy, as we just saw, is just n to the d times the summation of the Fourier coefficients modulo Fourier coefficients raised to the power of 4. Okay, this is a very, very important formula. Simple, but important formula in several areas of mathematics, including analytic number theory. Okay. Everybody with me still? No. That's not good enough. Tell me where I lost you, right? Because I know there are typos there. There's a typo.
I don't understand where this summation comes from.
This summation?
Maybe line.
Probably
yeah, maybe
the first equality.
The first equality, sure. Okay, no worries. Let's work it out. No worries. So we have a summation over n, okay? And then inside we have an indicator function of s. So what is this? N to the minus d over 2, summation of chi of minus x dot n, f of x, to the power of 4, correct? So you know where n to the minus 2d comes from? Because we simply take this and raise it to the power of 4. And now this is, so what does it mean to take a sum of complex numbers and raise it to the power of 4? It means to write this sum 4 times and put in some conjugates, right? Which means that this is equal to the summation over x, y, x prime, y prime. I'm just quadrupling this index. Okay, then n to the minus 2d is in front. Why am I reversing the order of summation? Because I can, and because I know in advance that if I don't, nothing is going to happen, right? And so we have summation over m, and here you have chi of m dot x plus y minus x prime minus y prime. And here we have, well, this is not f, this is 1 s of x. So we have 1 s of x, 1 s of y, 1 s of x prime, and 1 s of y prime. Okay, so now we just did it explicitly. And why can I write it like this? Well, I know there has to be 2 pluses and 2 minuses, and how we distribute them is immaterial because we can just exchange the roles of the letters, right? And there we go. Now we sum in n, and this sum is 0 unless this is 0, right? And the rest follows. Is it clear why this sum is 0 unless x plus y equals x prime plus y prime, or is it worth going over this? Should we go over this? Sure, let's do it. Why not? Let's see, does this board flip over? No. Okay, no problem. Can I erase this? Because I just want to use the upper part of the board. No worries. So let's take a summation of time and whatever x, and we're going to sum over all x, over all m. And the claim is that this is 0 if x doesn't equal to 0, and it's n to the d if x equals 0, right? So it's clear what happens when x is the 0 vector, n to the d if x equals 0. And by 0, I mean the vector 0, 0, 0, 0, 0, right? Okay, so this is a multidimensional sum. So let's assume that m is just in Zn and x is in Zn. In other words, d equals 1. Do you see why it's enough to assume this? By properties of exponentials, because this is chi of m1 x1 times chi of m2 x2. So we're just performing this sum d times. So it's enough to do this in one variable, right? So in one variable, what is it that we get? And so let's set box equal to 1 plus, how are we going to write this? Plus chi of x plus chi squared x plus plus chi n minus 1 x. Do you agree that I can do this? It's just properties of exponentials, right? Okay, so why am I calling this a box? So I cannot resist this story is because there was an interesting study in the Chicago public schools. So in first grade, students were given problems, box plus 2 equals 5, and everybody got it right. But a few years later, they were given x plus 2 equals 5, and the children started hiding under their desks, calling their mothers, et cetera, right? So, okay, if box is easier, I'm going to use a box. I don't have a problem. Okay, it's a true story. I know that you guys are not scared of variables, but still. Okay, so let's multiply both sides by chi of x times box. So this is equal to chi of x plus chi squared x plus plus chi n minus 1x plus 1. Because if you raise it to the power of n, it's e to the 2 pi I n over n. So you get 1. Okay? Now, and the assumption here is that x is not 0. If x is 0, this is nonsense, right? But if x is not 0, this is okay, because then chi of x is not 1. So then what we get is that box times 1 minus chi of x is equal to 0, and chi of x is not 0. So that tells us that box equals 0. And that's it. So that tells us that indeed, when we sum this in M, we get 0 unless x plus y equals x prime plus y prime. Does this clarify things a bit? Okay.
Maybe just a bigger picture. So we had this function we want to recover, and we have a support set S, yeah, and we have this inequality before that. For that, we can recover exactly if the product of measure of S and
size of E times the size of S is less than n to the d over 2. But the assumption involves Fourier frequencies. Mm-hmm. So if we want to prove something that involves Fourier frequencies, we need to have a basic understanding of how to work with the Fourier transform. And this is what I'm doing right now. Mm-hmm. So this is the big picture.
Okay.
All right. So we are looking, so we just showed that this additive energy is n to the d times the summation of the Fourier coefficients raised to the power of 4. And now what we do is we take, so remember our assumption. It's right here. So we take two of these powers and we estimate them out. Okay? And so the right-hand side is bounded by, this should be M. This is a plague. So the process of correcting slides never converges. It's at there. Okay. So you have n to the d, you have c Fourier squared, n to the minus d, size of s times the sum of the Fourier coefficients squared. So in other words, we took 4 of these, and we took 2 of them and estimated them out. Why did we do that? Because for this, we can use Plancherel. Because sum of the Fourier coefficient squared is equal to the sum of the function squared. So then this expression, these cancel. So this expression is just equal to C Fourier times the size of S squared. So what we just showed is that the additive energy of the set divided by the size of S squared is less than or equal to the Fourier constant squared. So what does this mean? That means that if the Fourier constant is a reasonable number like 5 or 10, and n is huge, that tells us that the additive energy is bounded by a constant multiple of the size of S squared. Why is that important? Because look at the definition of the additive energy. If you fix x, y, and x prime, you can solve for y prime, correct? That means that additive energy is never bounded by more than the size of S cubed. Also, it's always possible that x equals x prime and y equals y prime, or that x equals y prime and y equals x prime. So the additive energy is always at least twice the size of S squared. That's an almost complete lack of additive structure. So what we have just seen is that if you have a good Fourier bound on the Fourier transform with a reasonable constant, then you don't have very much additive structure. So we have established a relationship between the amount of additive structure in the set and the size of its Fourier coefficients, of its indicator function. Okay, so we have connected something arguably analytic with something, well, not arguably, with something definitely algebraic. Okay, so we have encoded additive structure in terms of the Fourier coefficient. So you asked a good question, what is the big picture? The big picture is recovering signals, but we are recovering signals which were sent using the Fourier transform, which means that we need to understand the Fourier transform. Okay, all right, let's keep rolling. So let me again give you an elementary point of view. Quick question, how much time do we have?
Like 20 more minutes. If it's 1 hour, but we can stay longer probably because you answer questions.
Maybe a tiny bit longer, yeah. Maybe like lecturing for another 20 minutes and then questions. Okay. So again, elementary point of view, you have already seen it, but let's cement it. So our signal is again a binary signal, and frequencies in S are unobserved. So we are going to repeat the same argument that we saw in the case of, in the continuous case, except here, it's always easier the second time and the setting is simpler. So we write it as an inverse Fourier transform of its Fourier transform, and we split it up into frequencies that we have and frequencies that we don't have, right? And you remember the game, we simply estimated the second term, we postulated that it's less than a half, and then we saw what happens. So let's do it. We simply applied the triangle inequality. Before, remember, we applied the restriction estimate. In this case, we're just applying the triangle inequality. So we bounded by n to the minus d over 2. So just, this is the term, right? The modulus of this term is 1. We're summing over the S size of S terms, and the indicator function Fourier transform of the indicator function is always bounded by the size of E times n to the minus d over 2. Okay, so that's what we get. When we combine them is n to the minus d, size of E times the size of S. Okay, so what if we assume that this quantity is less than a half? Then once again, we go back to the first term. You remember that game? We take its modulus, round up to 1 or down to 0, and we have exact recovery. Okay? And so this exact recovery using what we call the direct rounding algorithm, DRA. Okay? So, but what happens if we consider general signals? Okay. And so one of the questions that you raised before is, okay, so this works for binary signals or indicator functions of sets, which is the same. What happens for general functions? And this is where fun really begins. Okay. So the following results, so there's a very interesting history here. Until about 6 or 7 weeks ago, I believe that the argument I'm about to present is due to Donahoe and Stark. Donahoe and Stark in 1989 wrote a beautiful and very influential paper, which has many things in it. Among them is the argument I'm going to present. But it turns out that in 1973, which was 16 years earlier, Matorci and Zux wrote a paper in the French language. But in the US, we don't like learning foreign languages. So nobody read that paper. And somehow it flew under the radar. Even though both mathematicians are very strong, the Matorci and Zux. It's just nobody noticed somehow. But they proved the same result, and they proved it in the generality of locally compact abelian groups, which is no big deal because it just generalizes. Okay, so suppose that H maps Z and D to complex numbers. Then the classical uncertainty principle says that the size of the support of the function times the support of the Fourier transform is bigger than or equal to n to the d. This is the classical uncertainty principle, and I'm going to prove it's not hard. Okay? So suppose that f is a signal from Z and D to C, is supported in E in Z and D, with frequencies in S unobserved. This is the problem we've been discussing, right? Okay, so what does it mean? So it's actually the hardest part, or I don't know, the most interesting part, I would say, is just describing what it means that you cannot recover the function uniquely. What it means is that there's another signal which has the same support of the same size. Why not exactly the same support? Because then it actually requires you to know what the support was. This is more flexible. Here you just know that it has support of the same size. And the Fourier transforms agree except for S. We can't talk about what happens over S because the frequencies in S are missing. And F is not equal to G. If such a terrible G exists, then we don't have unique recovery. Okay? Now think back to your analysis class. If there's a terrible function G and you want to show that it equals to F, what do? You subtract G from F, right? Isn't this how every other problem in undergraduate analysis is solved? Okay, it's a slight exaggeration. All right?
Why do you require the size of support to be the same? What if it's a function of support of different size?
Well, when you do recovery, you have to fix what category you're working in. And this is the category we're working in, is that we know something about the size of the support, and we know something about the size of the frequencies that are missing, right? You can also make other assumptions, and we will do that later. But this is somehow the simplest.
So you know S.
You know S, absolutely. You know S, but you don't know the support of F. You just know its size. And so take H equals F minus G. Well, then the support of the Fourier transform is, of course, contained in S, because F hat and G hat agree away from S, right? Which means that H hat has at most the size of S non-zero entrance. And H has at most twice the supportive F non-zero entries. Why? Because H is F minus G. So if both F and G are zero, then H is zero. Okay? So if we apply the uncertainty principle, then we must have that the size of the supportive F times the size of the missing frequencies is bigger than or equal to n to the d over 2. So what if we don't want these terrible things to happen to us? Well, in mathematics, when you don't want something to happen to you, you postulate it out of existence. So we're simply going to assume the opposite. So you assume that the size of the supportive F times the size of the missing frequencies is less than n to the d over 2. And if that's true, then H must be identically zero, and the recovery is unique. Okay? What I'm not discussing in this lecture series, basically, right, there's a limited time, so there are choices that I have to make, is the recovery mechanism. There are many very, very interesting recovery mechanisms, but I decided not to discuss them. Okay? The mechanism described early in the Donahoe-Stark paper is terrible, but it tells you that there is a recovery mechanism. And what you do is you consider all possible functions with the support of that size, right? The moment you hear this sentence, you know that this cannot possibly be of practical use, right? Because this is an exponential time number. And then you solve the problem by the method of least squares. And they're better or worse. We're not discussing them. Okay, so here is so we actually have just enough time to sort of get to the point. The classical uncertainty principle is in general sharp. So I'm going to prove that it cannot generally be improved. But this is one of the most misleading statements I've ever heard in mathematics. Because even though it's in general sharp, if you choose a set at random, you're much more likely to get hit by lightning 3 times than you are to encounter a set for which the uncertainty principle is sharp. So there are very, very few of them. Okay? So, example, n is odd prime, and S is a k-dimensional subspace of Z and D. This just leads to an example that's easiest to visualize. There are many others. Okay? And also, there are other very interesting examples that are more algebraic. I decided to go with a more geometric one, right? Just a matter of choice. And so then if you compute the Fourier transform of the k-dimensional subspace, it's a direct calculation that I would encourage you to do. You will get n to the minus d over 2 plus k. K is the dimensionality. I took n to be prime in order to be in a vector space. So you get n to the minus d over 2 plus k times the indicator of the orthogonal subspace. Right? And we know what that means from elementary linear algebra. The size of the subspace times the size of the orthogonal subspace is n to the d. And that means that the classical uncertainty principle cannot be improved. Is this clear? Is everybody okay with the notation?
Just in discrete
Yes.
space, k-dimensional subspace, they are not like angled, they're just fixed in some, or they can be like at the angle, like it continuously.
But the k-dimensional subspace is still a k-dimensional subspace. It has their k-basis vectors.
It's not linear subspace, so just some points.
Oh no, here I even took a linear subspace. Here you can even take linear subspace. You could take an affine subspace too, but there's no need to illustrate this point. Just take the actual subspace. So it's a vector space of dimension k, which is a subspace of the vector space of dimension d. Right?
Yeah, okay, just
so,
for discrete.
Okay, so it's possible, correct me if I'm wrong, that in your linear algebra class, everything was done over R over C, is this correct?
Yeah.
But really, not much changes if you do it over Z mod n, where n is prime. Okay, so you can go over field. All right, and okay, and what we are going to see that in the presence of non-trivial restriction estimates, you have already seen what restriction estimates mean in the continuous setting. And soon you're going to see them in the discrete setting, that in the presence of such estimates, we can always do much better. So there's always a better uncertainty principle. Also, we are going to see, remember, we just introduced this additive energy that measured how much additive structure a set has. We're going to see that if your additive energy is even slightly non-trivial, you immediately get an improved uncertainty principle. And on top of this, we're going to see that for most sets with incredibly high probability, these sets do have non-trivial energy and do satisfy non-trivial restriction inequalities. That leads to a better uncertainty principle, which leads to a better signal recovery condition. And what I mean by a better signal recovery condition is less restrictive, which means you need to impose fewer assumptions on the signal in order to recover it exactly. Okay, so let's see. I promised to stop at 5:05. Is that okay, or should I stop sooner?
No. This will be just 60 minutes, and then I thought you asked us for another 10 minutes, no?
Right.
Continue.
Yes, it's fine to stop it.
So I'm still okay, but I'm not, okay, I haven't used up too much time. Okay, so I think I would like to go a tiny bit longer. So let's prove the classical uncertainty principle, and I think we'll stop there. And then tomorrow's lecture will be much more technical, but then you'll be well prepared for it. So h of x, so this is, we write h in terms of its Fourier transform. Remember what we're trying to prove. We're trying to prove is that if h is supported in a set E, and h hat, the Fourier transform, is supported in a set S, then the size of E times the size of S is bigger than or equal to n to the d. That's the uncertainty principle, which is a direct analog of the Heisenberg uncertainty principle, which I believe goes back to 1927 in the realm of physics, but the difference is merely notation. Okay? And so by the triangle inequality, you can bound modulus of h of x by n to the minus d over 2, the size of S, 1, and then we need to bound the Fourier transform. So we bounded it by another n to the minus d over 2, and then the L1 norm of h. This is okay? Okay. So now we sum both sides over x and e. The left-hand side depends on x. The right-hand side does not depend on x, because x inside this summation is a dummy variable. Okay? I think it's probably pedagogically more sound to use a different letter than x here, but you're okay, right? So you sum over x and e, and you get the size of e, and then you simply cancel the L1 norms. How do we know that we're not dividing by 0? Because if we're dividing by 0, then h is identically 0, and there's nothing to discuss, right? So we get the size of e times the size of s is bigger than or equal to n to the d. Okay, and the last thing that I want to say today is what we are going to dive into tomorrow, right? Is we are going to see that in the presence of non-trivial restriction estimates, we can get better uncertainty principles and hence better recovery conditions. Okay, and also let me just say a few words about the big picture. Okay, signal recovery problems have been extensively studied before in situations when the set of missing frequencies is random. Okay? However, there are interesting situations in practical signal recovery where you want to deal with deterministic sets of missing frequencies like spheres or paraboloids or planes. A restriction theory is a mechanism that combines both. Using restriction theory, it is relatively simple to study both random missing sets of frequencies and deterministic missing sets of frequencies. So Azita Mayeli and I embarked on this as a kind of a unification mechanism. Okay, and what is the restriction theorem going to say? You have already seen it in the continuous setting. In a discrete setting, we're going to say that S in Z and D satisfies the PQ restriction estimate. P is at least 1, but at most Q, with norm CPQ. If for any function f from Z and D to complex numbers or a signal, whatever you want to call it, then the normalized LQ norm of the Fourier transform is bounded by CPQ n to the minus D over 2 and not normalized LP norm of the function. Okay? And what we are going to see tomorrow is a series of results showing that a non-trivial restriction estimate implies an improved uncertainty principle with consequences for signal recovery. And I think this is good enough for today.